Okay, welcome to the physics green screen. I'm Santos, for those who don't know me. This is for Physics 151 at Simpson College. This is an introductory course in physics. It's algebra based, and we're going to be answering some questions from students. Okay, here we go. Question number one. A question that I had was, why is the SI unit for mass kilograms instead of grams? In both biology and chemistry, we used the SI unit of grams, and I found it very interesting that physics decided to differ from that. Is it because it makes it easier to convert to newtons, or did physics just try to be a little more unique? Haha. I don't actually know why physics chose kilograms rather than grams. I mean, it certainly does make it easier to convert to newtons from kilograms, simply because you have, the newton is a kilogram meter per second squared. But I'm not sure. It's possible that physicists do just like being different. The next question. Yeah, in the reading, you mentioned using the Google search bar for making our calculations instead of a calculator. Is it easier to use the search bar because you do not have to make as many unit conversions? Sometimes when you get really into an example, those conversions seem to be endless. Usually at the beginning of a physics class, you have your students learn how to convert from meters to kilometers to centimeters. We still do that here, but you're not going to live that long, and we live in the 21st century, and there are calculators that'll do this for you. One of these is the Google search bar, which can be used as a calculator, and you can type in your units right in there, and it'll automatically convert to SI units. So we are going to stick with the Google search bar for that reason. Again, it's just because it makes life easier. As the student put it, the conversions do seem to get endless after a while, and you don't want to spend your time doing this. You want to do the fun parts of the problems. Next, when talking about units, where did the term dead king's foot originate? Does it have historical significance, or is it a term that you coined? It is not a term that I coined. I think I saw it in a book called The Mechanical Universe. I suspect the historical significance is if you're looking for a unit of measurement and the king is collecting taxes on property, based on how big your property is. Perhaps it's being measured by the king kind of marching off and figuring out how many feet are in your property. But I don't actually know specifically where the term comes from. Next question. The reading said that the value of m does not affect the shape of the graph. We're talking here about the the slope of a y equals mx plus b curve. M does not affect the shape of the graph, so we aren't worried about the slope. Does this mean that for physics, we're purely interested in what the line looks like and won't worry about any of the area underneath? It seems weird to me that the coefficients don't matter. I don't want to say that the coefficients don't matter, but a lot of times in physics, you're interested in, the word we use is how the function scales. Does it scale linearly? Does it scale as the distance squared? If that's what you're worried about, if you're worried about the shape of the function, then the slope doesn't matter. Whether I put m equals 1 or m equals 2, I'm still going to have a straight line going up. That being said, what you want to do is calculate an exact numerical value, of course the slope is going to matter. You're going to want to use the slope there. But if we're talking about just the relationship between quantities, which is, I think, the more important thing in physics, then that the exact value is not going to matter. That's why one of the things physicists like to say is you want to solve in variables. Well, it's because the variables are more important. How one physical quantity depends on another is more important than the exact specific value you get for final position or whatever you happen to be looking for. Next, In the last paragraph of the reading, it had a little tidbit about mammals living for 1.5 billion heartbeats. If that is so, do people with naturally faster heartbeats die sooner, or do other factors, i.e. diabetes, heart disease, outweigh this simple fact? Correlations with overall physical fitness and age span, etc. Can you tell I'm an exercise science major? Yes, I can tell you're an exercise science major, possibly because you asked me that. I would say, well, when we're considering this law, so this is an example of a type of scaling law. This is an average over many mammals. It doesn't really apply within a given species. So if you go to your doctor and you have a slow heart rate, they'll probably tell you that that's a good thing, because what it means is that your heart does not need to pump as often. If you have a strong heart, it can get a lot of blood coming out of it without actually beating as much. So, if your heart doesn't have to work as hard, that means you're in pretty good shape. So generally, people with slower heart rates usually tend to live longer. I don't necessarily know that applies here, though, because what we're talking about is different species of mammals, not what heart rate does in an individual species. Obviously, if you have a small if you have a small child who's 1 years old, and that child dies early, it's not going to have made it to the 1.5 billion heartbeats, not anywhere close. So there's a lot of other factors that come into play here. It's not just that you make it 1.5 billion heartbeats. Next, am I going to die mid-course from sheer confusion? Probably not, but maybe. Next, in regard to the pigeon problem, can it even be done without knowing what hundreds is defined as? So this is in reference to a problem where we pulled from, I think it was a newspaper article, where you have hundreds of pigeons being hunted, you have a billion pigeons being hunted by 100 hunters, or it says hundreds of hunters. And does this article make sense? Is it actually feasible? And then the question goes on. Again, this does not compute for me. To me, there is a massive difference between 100 and 999, both in the hundreds. So I don't understand how you can determine the number without arbitrarily choosing. Or is that the point? That is kind of the point here. So it turns out that with any experiment or physical quantity, there's a certain range of numbers that are reasonable. And once you get outside that range, the numbers just become completely unreasonable. So anywhere between 100 and 999 hunters is a reasonable estimate for, if you're given the number, if somebody says, well, we have hundreds of people showing up to this event, you expect that it's between 100 and 999. That's a good estimate. But anywhere between that, it turns out for this particular problem, is just completely unreasonable. We had a billion pigeons. Even if you have 1,000 people, that's saying they're each getting 1 million pigeons that they're hunting. So it's just an unreasonable number, no matter which number you choose. And that's one of the big points of estimation, is that it's kind of a BS detector. So you don't have to know exactly what the right number is to get a rough idea of whether or not something should be feasible. And there's a few more estimation questions we're going to be seeing throughout the course. Hopefully you'll get a better appreciation for that as time goes on. They start to be really fun problems. Next, I have one maybe silly question. For exam, by the way, silly questions are my favorite type. For exams, will we be responsible for an equation sheet or just a mental one? That's not a silly question. No, you will be responsible for an equation sheet. So in physics, I already have lots of equations here. You've got so many equations, I don't expect you to remember the exact form for each of them. You will have an equation sheet. Good idea if you start writing down equations now throughout the semester and just adding to it as we cover new topics. because they're going to add up pretty quickly, and you don't want to have to make an equation sheet right before the test. Next, is dimensional analysis just the art of why different measurements can't be added together, or is there more to it? That's all there is with dimensional analysis. It literally just means looking at the dimensions and seeing if you're getting the right type of dimensions. So for example, I can add something in meters to something else in meters. I cannot add something in meters to something in seconds. Those are just fundamentally different quantities. Length is different than time, so it doesn't make any sense to add quantities with different units. Next. The book talks about the particle model to help solving problems. Do you automatically place the dot in the middle of the object, or does it depend on the object? And there's a follow-up to this one. What is lost when you look at the object as a whole compared to just a particle? Is it just a way to simplify the motion diagram? Going back to the whole idea of estimation and approximation, in physics, we're all about coming up with simpler models. So if I'm dealing with an actual object that has some shape, say I have a cube, that cube has different orientations that I can put it in. It's simpler if I just want to talk about the location of the cube and not the orientation of the cube, so not which way it's angled. It's easier just to treat it as a point object. So what we'll do is we'll, at least for the beginning part of this course, and probably into the Physics 152, the second part of this, we're going to treat all objects as pretty much being point objects. So if you want to put the dot in the center of the object, that's a good place to put it. The center of mass is actually a little bit more precise, but we haven't talked about that yet. But for now, just think of it as an easy way to represent the object. We're just going to consider exactly where it is by taking the middle of it. Up next, while reading section 1.1 in our text, I was wondering if the particle model of a motion diagram can show direction to, or just a change in speed. We're going to deal with vectors in the next course, where we've moved that back to the second semester. But the particle model can show speed, can show changes in direction in addition to speed. So yes, so if an object is moving this way, and I'm looking at where it is at different time intervals, and then the object starts moving up, I can tell that. I can see that in the motion diagram. It might be a little harder to see if it changes directions and starts moving backwards, because then the dots might overlap. But in principle, you can show changes in direction in the particle model, in the motion diagram of a particle model picture. Up next, let's see. So if you are given a lengthy word problem that includes a lot of numbers that are unnecessary to the calculation, do you still refer to the value with the lowest number of significant figures? Or do you set up the problem and then pick between the values that you actually use? So in class, we came up with this simple rule for significant figures. Namely, you multiply a bunch of numbers together, the number that goes into the calculation that has the least number of significant figures, you use those significant figures in your final answer. So you use, let's say you're multiplying a number with 2 significant figures, and then another number with 10 significant figures. Well, the end calculation, the result should only have 2 significant figures because they're the thing that has the most uncertainty. They're going to be determining how uncertain your final answer is going to be. Now, if there are other numbers that show up in the problem, but you don't actually use those to do the calculation, it doesn't affect the number that you've calculated. So you don't want to, if you have another number that only has 1 significant figure, but you didn't use that in the calculation, you'd still use 2 significant figures because you're only concerned with the numbers that actually go into the calculation. Next, when working with significant figures, should we round to the number with the most number of significant figures before we start the actual work? Or should we round the answer to the correct number of significant figures at the end? There might be different schools of thought on this, but I like to keep all the accuracy until the very end. So I would say only do all your calculations in your calculator, and then only at the end do you round off and report the number of significant figures correctly. I'm a bit confused with the concept of positive versus negative displacement. Because regardless of the direction traveled, there is still distance covered. So I'm lost with subtracting this number. I'm lost with subtracting from this number were the target to be moving in different directions, in two different directions. So the basic idea behind displacement is that I could be moving to the right, or I could be moving to the left. Now I could move 1 meter to the right, I could move 1 meter to the left. But the point with physics, which is a little bit different so in everyday life I say, well, I moved 1 meter to the right, or I moved 1 meter to the left. In physics, we try to treat things more mathematically. So rather than saying to the right or to the left, we say in the plus direction or in the minus direction. It gives us a way to take into account the left or right motion explicitly into the math with the plus or minus sign. So just think of plus and minus as a shorthand for whether it's moving to the right or to the left. Since displacement is a vector, we want to write down the direction of motion, not just how far we moved. Next, the uncertainty principle is kind of confusing to me. Me too. I thought you could use velocity to predict the exact position of an object at any time. If what we're talking about, well, first of all, in real life there are no exact positions. Every number has some uncertainty to it. Anything I measure, I can never measure anything exactly precisely. Just practically, my meter stick only goes down to millimeters. And even if I built a better meter stick, it would still only go down to a certain size. So there's always some uncertainty as a practical matter. And in fact, the uncertainty principle is, you can get much more precision even with the uncertainty principle than you really need. I mean, how do I want to say this? The uncertainty principle says that the uncertainty in position times momentum has to be of the order 10 to the minus 30, I think kilograms meters squared per second. So what that means is that, that 10 to the minus 30 is a ridiculously tiny number. You're never going to have that much accuracy in a measurement in anything we're going to do in introductory physics lab. So practically the uncertainty principle doesn't matter for what we're doing. Fundamentally, from a fundamental picture, the uncertainty principle places a limit on how accurately I can know position and velocity simultaneously. We're going to talk more about why that is next term. But what the uncertainty principle says, it's not that you can't measure position and velocity. It's that if you have a particle with a certain position, it doesn't have a definite velocity. And that is a tricky point. But I want to leave that for second semester because I could go off for hours talking about this and how interesting it is. But moving on. Since it's true that our height lying down is about half an inch longer than our height standing up because of gravity, does atmospheric pressure also make us measurably shorter? So in class we talked about how it said that astronauts, when they go into outer space, get noticeably taller because, maybe 1 or 2 inches taller because there's no gravity kind of pulling them down and compressing their body. And we did an experiment to test this. We had a student who measured their height standing up and then their height lying down. And there is a significant difference between those two different heights. Does atmospheric pressure affect it? I don't know, but I suspect so. So atmospheric pressure is some ridiculous number like 2,000 pounds per square foot. I forget the exact number, but it's a huge amount of pressure. Later on we'll talk more about pressure, and we're gonna use atmospheric pressure to crush a metal can. And atmospheric pressure is just huge. It just crumples the can pretty easily. But So the short answer to your question is I suspect that it does make you a little bit shorter by compressing you. A quick way to see this is you just take a vacuum cleaner and stick it on your arm. You see your skin start to come out. Well, you're taking that atmospheric pressure away, so your skin's getting a little bit bigger. I don't know how much bigger we would be in the absence of atmospheric pressure. We could put some of you in vacuum, but you'd die and have lots of other problems. Atmospheric pressure is a useful thing, even if it does make us shorter. The next question I love because it's so deliciously meta. The question is, how many times per day would you say we use estimation? They want me to estimate how many times we use estimation. A lot. We use estimation in a lot of different ways that we don't even think about. So somebody asks me what time it is, and I look at the clock in the back of the room that you obviously cannot see, and it says 10, I would say it's 10:30. But really, it's 10:37 and 16, 17, 18 seconds. Now, if I say 10:30, it's not like I'm lying by telling you that it's 10:30. If I leave off the 7 minutes and 15 seconds, there's some uncertainty there. All I'm doing is making an estimate. We do this all the time in everyday life. Somebody asks, well, how long is it going to take to get to work today with traffic? You say, yeah, about 15 minutes. It's not exactly 15 minutes. Somebody asks you, is it walking distance from here? How long is it going to be? You say, yeah, it's about a mile. So consciously or unconsciously, we're always making estimates in our heads. And it's good if we get in the formal practice of doing it, so we pay attention to what those numbers actually mean. Next question. Let's see. What happens with significant figures if it isn't just multiplication or addition, but a combination of the two in a given problem? What should you do if you're doing different operations? Please excuse my dear Aunt Sally. Parentheses, exponentiation, multiplication and division, addition and subtraction. You just want to work in the orders of, do the normal orders of operation for algebra. And if you stick with that, you should be fine. Just keep track of the number of significant figures after each step. Is saying the word per fairly similar to saying divided by, since in division you're trying to set things into groups? I think what this person is asking is, in physics we say miles per hour, meters per second, kilograms per meter cubed for density. Per just means divided by. That's all it really means. Is the only difference between speed and velocity that velocity includes direction? Yes, that is the only difference between speed and velocity. Next question. Is there an actual use for order of magnitude estimation? To me, it seems very inaccurate, and two people could have completely different estimations. Two people could have different estimations, but I would disagree with the statement that they are completely different. So, if I were to estimate your height without knowing anything about you, because you're watching this on YouTube, I would say you're about 5.5 feet tall. Now, you could be 5 feet tall, you could be 6 feet tall, you could be 3 feet tall, you could be 7 feet tall, but you are not going to be 60 feet tall. That would be very surprising. So estimation may not give you the exact right number. Between 3 and 7 feet, though, I'm pretty sure you're somewhere between those values. And that's what estimation really does. Now, that might not seem impressive if we're talking about guessing someone's height or weight, but if you're talking about the number of grains of sand in the universe or the number of stars in the sky, order of magnitude estimates are sometimes the best accuracy that we can get. And so they're very useful for that way. They also serve as kind of an idea tester. So I know, if I do an estimate for how much money, I want to buy a new house and I want to estimate how much money is going to go into it, I want to know if I'm going to be spending, an extra $20,000 putting work into fixing up the house, or an extra $200,000 putting work into the house. So it gives us the fact that it gives us a rough idea of what are the worst possible scenarios makes it a very useful calculational tool to have in your toolkit. Let's see. When talking about uniform speed, does that mean that multiple objects are starting at and moving at the same speed together? No. So uniform speed means just that I have one object and it's moving at the same speed for all time. So if it starts moving at 5 miles per hour, it stays moving at 5 miles per hour. It never changes its speed. That's all that uniform speed means. Next question. Will we use a positive velocity to indicate motion to the right or for vertical motion upward, and negative velocity for an object moving to the left or downward like the book does? That seems to be standard convention in physics class, and I will try to stick to it for the most part, but it's entirely up to you whether you want to define right as positive and left as negative, or vice versa. As long as you're consistent, the calculations will still work. There's nothing about the right, moving to the right that inherently makes it more positive-y. Let's see. Will we need to memorize prefixes and units, or will they be provided during tests and quizzes? You should know the common ones. So you should know the difference between a meter and a centimeter, and a meter and a kilometer. More esoteric units like light years, which you might even be able to figure it out if you think about what a light year means. But I do not expect you to remember those. If there's anything, any really weird units like BDUs or things we haven't seen in class, I will provide those on the test. And I think that's it. Thank you for watching, and hopefully you've gotten a bit out of this and learned something, and hopefully we'll see you next week.